Hello everyone. I am Master Vardhaman Uday Kerkar from class MSc Mathematics Part 1 of Government College of Arts, Science and Commerce, Sanquelin. So today we are going to work with the ring of continuous functions from the real numbers to the real numbers. This ring is usually denoted by C of R. Now let's have a look at our question. The question is, prove that f belonging to C of R such that f of 0 equal to 0 is a maximal ideal of C of R. The second part of the question is, f belonging to C of R such that f of 0 equal to 0 equal to f of 1 is not a maximal ideal of C of R. And the third part of the question is that, can you generalize the above results? In order to solve this question, first let's recall some definitions. The definition of ring. It is a set equipped with two operations, addition and multiplication. But in our case, the ring is C of R, which is all continuous functions from R to R. Addition and multiplication are done pointwise, that is, f plus g of x equal to f of x plus g of x, and f into g of x is equal to f of x into g of x. Next is the definition of ideal. An ideal of a ring is a subset that is closed under addition and also closed under multiplication by arbitrary elements from the ring. Next we have the definition of maximal ideal. A maximal ideal is an ideal which is proper but not contained in any larger proper ideal. Equivalently, an ideal M is maximal if and only if the quotient ring R modulo M is a field. And this last fact will be very important for us to solve this problem. Now, another thing which we have to recall is that, what does quotient ring mean? When we write something as C of R modulo MA is isomorphic to R, what does that exactly mean? It is called a quotient ring. It means we are taking all continuous functions and considering two functions equivalent if they agree at the point. So the statement says, the quotient ring obtained from functions vanishing at that point behaves exactly like the real numbers. So now let's prove the first result, that is f belonging to C of R such that f of 0 equal to 0 is a maximal ideal of C of R. But before starting this, let's write some introduction about the entire problem, that is, let C of R be the ring of all continuous functions from f such that it is from R to R. Since addition and multiplication are positive, therefore, as discussed earlier, f plus g of x equal to f of x plus g of x and f into g of x equal to f of x into g of x. So now we will use the evaluation map at a point A belonging to R. So let's look at the set M0, which is equal to f belonging to C of R such that f of 0 equal to 0 is equal to kernel of EV0. Now we have to show that EV0 is onto. It is clearly a ring homomorphism, that is, it respects addition and multiplication because evaluating at 0 distributes over both. Also, the kernel map of this is kernel of EV0 is equal to f belonging to C of R such that f of 0 equal to 0, which is we can term as M naught, which we have already termed as M naught. And to check if it is onto, then for any real number r, the constant function f of x equal to r is continuous, and f ev0 of f is equal to r. Therefore, ev0 maps onto all of r. Therefore, it is onto. So, every real number appears as an image. So, the image is all over R. So, by applying the first isomorphism theorem for rings, which says this, we get C of R modulo M naught is isomorphic to R. Now we can conclude that since R is a field, the quotient is a field, which means M naught is a maximal ideal. So we have proved the first part. Now to prove the second part, which is to prove that f belonging to C of R such that f of 0 equal to 0 equal to f of 1 is not a maximal ideal of R. That is, the functions vanishing at 0 and 1 are not maximal. We have to show that. So let I equal to f belonging to C of R such that f of 0 equal to 0 and f of 1 equal to 0 equal to kernel of EV at 0, 1. Now we have to show that I is not maximal. So we need to find a strictly larger proper ideal containing I so that the result will be proved. In the first part, we had defined M naught as f belonging to C of R such that f of 0 equal to 0 is equal to kernel of EV naught. Now, since I is a subset of M naught and there exists a function in M naught which is not in I, we can take an example, that is, if g of x equal to x, then it satisfies g of 0 equal to 0, but it doesn't satisfy g of 1 equal to 1 because it is not equal to 0. Since I is contained in M naught and there exists a function in M naught which is not in I, therefore, M naught is equal to f belonging to C of R such that f of 0 is equal to 0 is an ideal that properly contains I. But is this containment strict? The answer is yes. Because for example, if we take g of x equal to x, then g of 0 is equal to 0. So g belongs to M naught, but g of 1 is equal to 1, which is not equal to 0. So g cannot belong to I. And this clearly shows that I is a subset of M naught properly. And since M naught itself is a proper ideal, I is contained in a strictly larger proper ideal. Therefore, I cannot be a maximal. And this proves the second part. Now let's prove the third part, that is the generalizing of the above proved results. Means the results which we have proved, the first two parts of the question. Now we have to generalize those statements. So let's generalize this. We started with two cases. That is, the first one was one point condition, that is M naught is equal to f belonging to C of R such that f of 0 is equal to 0 is maximal. And the second one was 2 point condition, that is if I is equal to f belonging to C of R such that f of 0 equal to 0 is equal to f of 1 is not maximal. Now let's generalize to arbitrary set of points. So case 1, is vanishing at a single point. So, for any A belonging to R, define MA equal to F belonging to C of R such that F of A equal to 0. Now let's consider the evaluation map EVA, which is this, and EVA of F is equal to F of A. Kernel is exactly MA. That's why for the first isomorphism theorem, we can conclude that C of R modulo MA is isomorphic to R. And this implies that every single point vanishing ideal MA is maximal. Now let's take the case 2, that is vanishing at 2 or more points. So let S equal to A1, A2, an be a finite set with n greater than or equal to 2. Let's define Is, which is equal to f belonging to C of R, such that f of ai equal to 0 for all I from 1 till n. Let's define the evaluation map phi from C of R to Rn such that phi of f equal to phi of a1, phi of a2 till phi of an. So the kernel is exactly Is, and by the first isomorphism theorem we can say that C of R modulo Is is isomorphic to Rn. But we have said that it is a finite set with n greater than or equal to 2. So for n greater than or equal to 2, Rn cannot be a field because it has 0 divisors in it. And that's why we can conclude that Is is also not a maximal ideal. Now in case 3, let's talk about infinite sets. So if S is a subset of R has infinitely many points, then Is equal to F belonging to C of R such that F of S equal to 0 for all S belonging to capital S, then Is is contained inside every single point ideal MA for A belonging to S. And since at least one of those MA is strictly larger, therefore Is is also not a maximal ideal in this case as well. So finally, we can conclude that maximal ideals of the form f such that f of a equal to 0 correspond exactly to single point a belonging to R, and ideals of functions vanishing on two or more points are never maximal. So this is the generalizing statement which we can make in this problem. So summarizing the entire problem, we can say that the set of continuous functions vanishing at one point forms a maximal ideal. Also, the set of functions vanishing at two or more points is never a maximal. And in general, all maximal ideals of C of R are exactly of the form MA, which is equal to F such that F of A equal to 0 for some real number A. And this completes the entire proof and entire solution